prove the first case. Okay, so we need to prove that I equal the open interval alpha beta, right? Therefore, we need to show that once the left hand side is a subset of the right hand side, and the right hand side is also a subset of the left hand side. Okay, so we take x in the left hand side, that is I. Then because alpha is the influence of I, and the beta is the supplement of I, this implies that any x in I, x will locate between alpha and beta. Okay, so since as we assume alpha is not an element of I, and also beta is also not an element of I. This is our assumption right here. So x belongs to the so we must have alpha less than x less than beta, because x belongs to I, but alpha and beta are not belongs to I. So x could not equal to alpha or equal to beta. Therefore, x is strictly greater than alpha and less than beta. This implies that x belongs to the open interval alpha beta. So we have proved that I is a subset of the open interval, right? So we need to prove the other side of the inclusion relation. So for x in the open interval alpha beta, then we have the infiniment of I, which is our alpha, less than x less than beta, because x belongs to the open interval alpha beta. Therefore, alpha less than x, x less than beta. Beta is the supplement of I. So what will we have? Let's draw a picture. This is alpha, this is beta, and x is here. So by the definition of infiniment and supplement, we see that there exists alpha prime here, and the beta prime here. Because alpha is the infiniment of I, and x is an element. No, I don't know whether x is belong. I don't know whether x is an element of I. But since alpha is an infiniment of I, so so there must be an element of I denoted by alpha prime, which is located between alpha and x. And also we have beta prime located between how to write this? Alpha prime. Okay, and similarly, we have beta prime belongs to the intersection of I and the x beta interval. Okay. Do you have any question about this? You see, if there is no element, if there are no element of I within this interval, then the infiniment of I will not less than x. So this is a contradiction to the fact that alpha is the infiniment. Okay, so there must this contradiction implies that there must be an element of I located between alpha and x. That is our alpha prime. Similarly for the beta prime. Okay. Now our I is path connected. I is path connected. Therefore, by definition, there is a continuous map denoted by gamma from 0, 1 to our I, such that this is a path in I. This gamma is a parameterized path in our set I. So which endpoint alpha point and beta point. Gamma 0 is alpha prime, and gamma 1 is beta prime. So because gamma as a continuous map defined in the on the interval 0, 1 and take real value I is a subset of I of R. By the intermediate value property of the continuous one variable single variable continuous functions, there exists a tau in the interval such that gamma tau is x. Why? Because x is located between alpha prime and beta prime. Yeah. Because x. Okay, so there must be a tau such that gamma tau equals x. But gamma is a map into the set I. So gamma tau x equals gamma tau. This and gamma is mapped into I. So this implies that x is belongs to I. So x. So x belongs to I. So we have proved that for any x in the open interval alpha beta, x belongs to I. So this proves our proposition, the first case. Okay. And now I will show you some example of other pathwise connected set in higher dimensions. In one dimension, we already clear that only the intervals are pathwise connected. How about higher dimensions? Higher dimensions are much more complicated. But we can have some examples. Suppose D is a subset of which is pathwise connected, and f is a continuous function defined on D. Then we have the subset in n plus 1 dimension. The graph of f. This is a new concept, graph. What's the graph of f? We denote it by GF, which consists of a point of the form fx, xfx, where x belongs to D. This is called the graph of f, which is a subset of Rn plus 1. Because the x here, x belongs to D, so x is an n-dimensional point. X has n coordinate, and fx is a real number. Altogether, the point xfx has n plus 1 coordinate. Therefore, such point consists of our GF, a subset of Rn plus 1. Okay. So this graph, we declare that this graph is pathwise connected. Okay. For the graph of functions, I hope you be familiar with these things. For example, for the case n is 1, then D is a subset of R. For example, D is here, and a function, the graph of the function is this curve. So this is GF. It's a subset of R2, right? Similarly, for for the two-dimensional case, so this is x, y, z, and our D can be a disk in unique disk in the xy plane, and the graph of this of two valuable functions is this is a surface in R3 in three-dimensional space. For example, the upper half sphere is the graph of this function z equal 1 minus x squared minus y squared. I believe you know this from analytic geometry. Okay, so our example here is a higher dimensional case. Okay, in our homework, we also study the case that F is not mapped into R, but into another Euclidean space of higher dimension, Rm. We have an homework assignment, study the graph of this map from D to Rm. Okay, so let's go to the proof of this example, the conclusion of this example, that the graph is path connected. How to prove this? So proof. Let AFA BFB be 2 points in the graph. Of course, the graph, every point in the graph can be is of the form x fx. So x equal to a, x equal to b. We get 2 points of the graph. Okay, here a and b are points in D. So our condition says that D is pathwise connected. This condition is of course very crucial. So we need to use the pathwise connectedness of the domain of definition D. Since D is pathwise connected, by definition, and the AB are 2 points in D, there is a path in D joining the point A and B. There is a path in D joining A and B. So this is a continuous map gamma from 0, 1 to D. Gamma is a parameterized path in D. The initial point is A, the end point is B. Okay, so this is the graph. This is the domain D, and A, B is here, and this point is A, F, A, and this point is B, F, B. Okay, so AB can be connected by a path. That is our gamma. So we need to, our purpose is to find a path in the graph joining AFA and BFB. This is what we want. Obviously, we can construct such a path using this gamma, right? So we defined a capital gamma to Rn plus 1. How to define this gamma? Obviously, capital gamma T will be gamma T, F gamma T, right? Such point obviously is contained in for any t in the interval 0, 1. Obviously, gamma t belongs to the graph of f because the pointer in gamma t is of the form a pointer in D and the value of f at that point. Okay, so gamma t is a pointer for every t, gamma t belongs to the graph. And gamma 0 is small gamma 0, f small gamma 0. But small gamma 0 is A, so this is AFA. Is our point, one of our point choose at the very beginning. Similarly, gamma 1 is another point, BFB. Okay, so this capital gamma, given any 2 point in the graph, this capital gamma is a path in the graph joining these 2 points. So by definition, the graph is pathwise connected. So this proves this example. Okay.